Okay, we have one more section that we need to cover in Chapter 8. Sorry, my voice is going a little bit today, guys, so we'll just have to make do. We're talking about Section 8.5, which begins on page 516. And this is the inverse trig functions. Now, we've been using the inverse trig functions to solve our trig equations. So, for example, we could have something like sine of x is equal to 2/3. So we want to solve sine of x is equal to 2/3 for x on this interval. So the open interval from 0 degrees to 360 degrees, let's say. So we're going one time around the circle in degrees. And so what we did is we got sine by itself, which it already was, and then we would say that x is equal to the inverse sine of 2/3. So we take the inverse sine of both sides to get rid of the sine. This is something that we then punch into our calculator. So the first thing I need to do is double check to make sure I'm set to degrees, which I am. The next thing we do is second function sine. Don't forget the parentheses because we want to take the inverse sine of the entire value, 2/3. And that gives us 41.81 degrees. The question is, why doesn't our calculator give us the other solution? There's another solution between 0 and 360 degrees on our circle. So we know from using reference angles, 41 degrees is in here somewhere, 41.81 degrees. Our reference angle is 41.81 degrees. Sine is also positive in quadrant 2, so we have another solution over here at 41.81 degrees. Reference angle, that's going to be 180 degrees minus 41.81 to get this solution. To go with that one. So 180 minus 41.81 is going to give us 138.19. The question is, why doesn't the calculator just automatically do that for us? And the answer is that the calculator is not capable of doing it for us. And so we need to talk about why that is so that you guys understand the concept behind what's going on with our trig functions, our inverse trig functions. So let's take a look for just a moment at our sine curve. So on our sine curve, we know it looks something like this. All right. And then it repeats itself. Etc. The problem is, guys, that while sine is a function, it passes our vertical line test. Notice that inverse sine will not be a function because it does not pass the horizontal line test. Okay, the horizontal line will hit the curve an infinite number of times. As soon as it hits more than once, we know the inverse is not a function. What are the implications of that? Well, that would mean that every time we punch in inverse sine of 2/3, theoretically our calculator could give us a different answer, an infinite number of different answers. That would be completely 100% useless to us. We need to always get the same answer every time we punch it in. And so in order to accomplish that, what happens is we limit the sine function. And what we limit it to is this piece right in here. Let me just kind of darken it in red here so we can really see it standing out. This is the piece that goes from negative pi over 2 to positive pi over 2. By limiting the sine curve to just that piece, when we look at the inverse function, notice that not only will it pass the vertical line test still, but it will now pass the horizontal line test. We get all of our positive y coordinates, our positive sine values from this piece, our negative sine values from this piece. So negative pi over 2 to 0 is quadrant 4. 0 to pi over 2 is quadrant 1. And so if we look at the unit circle, what we're doing is we are limiting the domain, the range, the outputs of our inverse sine function to the region between negative pi over 2 through 0 to positive pi over 2. In other words, negative 90 degrees to positive 90 degrees if we're talking about degrees. So that means that whenever we hit inverse sine on our calculator, the only answer that the calculator can give us is between negative 90 and positive 90, numerically, not just location-wise, numerically. Okay? 280 degrees is not an answer that this can give us. 280 degrees is fine location-wise. It's down here, 10 degrees past 270. But 280 degrees is not between negative 90 degrees and positive 90 degrees, negative pi over 2 and positive pi over 2 numerically. So what it would have to do is if we were looking for something like 280 degrees, what we would have to do is instead we'd have to go backwards and we would have to call this thing negative 80 degrees. That would be a value that our calculator could give us. The calculator is not capable of giving us 280. So this is a very important concept for you guys to understand, is that all three of our main trig functions, sine, cosine, and tangent, when we are looking at the inverse functions, we limit the range of those inverse functions, so that it's only capable of giving us certain outputs. And the reason we do that is for consistency. So what this means is that for inverse sine of x is always going to be between negative 90 degrees or negative pi over 2 and 90 degrees, positive pi over 2. Inverse tangent works the same way. Inverse tangent is always going to be between negative 90 degrees and positive 90 degrees, or negative pi over 2 and positive pi over 2. Quadrant 4 and quadrant 1, we get our negative tangent values from quadrant 4, we get our positive tangent values from quadrant 1. So these two operate in this region here. Inverse cosine, however, goes between 0 degrees and 180 degrees, 0 radians and pi radians. Why? Because if we looked at the same region for inverse cosine that we do for sine and tangent, cosine is positive here and also positive down here. We wouldn't get our negative values from anywhere. So that's why we can't use the same two quadrants. We have to use these two quadrants, going from 0 to positive 180, or 0 to pi. We get positive cosine values from quadrant 1. We get negative cosine values from quadrant 2. So this is a very important concept to understand, that the calculator, for consistency's sake, is only capable of giving us certain outputs. And that's why we are required to use reference angles to find any other suitable solutions to trig equations. So it's very important that you guys understand that we're dealing with quadrant 4 and quadrant 1 here, and we're dealing with quadrant 1 and quadrant 2 down here. Okay. Let's take a look at how we're going to use these things now. We are only going to look at one particular type of problem. There's two variations on it. We're not going to do any graphing of inverse trig functions. We're not going to worry about that. We're going to worry about evaluating. And what we're going to do is we're going to evaluate things like inverse sine of pi over 6. Well, what most people do is they say, oh, look, we have an inverse, and then we have the original function. These just cancel each other out, and it gives us an answer of pi over 6. Well, for this particular problem, that is certainly true. But that is not the way you want to go about doing these, because that will only be true for certain angles, because remember, what we're doing is we're doing the inverse sine of some value. And remember that inverse sine can only have outputs that are between negative pi over 2 and positive pi over 2. Now, pi over 6 falls in there. So this works. But what happens if you have inverse sine of 7 pi over 6? Well, what a lot of people will do is just cancel those out, and they'll write down 7 pi over 6. And the problem is that is 100% wrong, because 7 pi over 6 is over here in quadrant 3. It's not in quadrant 1 or 4. And it's certainly not between negative pi over 2 and positive pi over 2. So therefore, this is not correct. So I want you guys to understand the proper way to do these things. If that angle is a quadrant 1 angle, then you're safe doing that. But again, I don't recommend it. I want you to understand the concept, the way to approach these. I said there are two variations on these problems. We're always going to have an inverse function and a regular trig function in the same problem. And they're going to be composited in one of two ways. Either the inverse on the outside and the regular one on the inside, or vice versa, with the regular one on the outside and the inverse on the inside. So right now we're dealing with the ones where the inverse is on the outside. And what you want to do on these is you want to look at inverse sine of 7 pi over 6, and you want to work this from the inside out. Sorry about that, guys. I dropped my microphone onto my tablet here. Okay. We want to work it from the inside out. 7 pi over 6 is here. The coordinates at 7 pi over 6 are negative rad 3 over 2, comma negative 1/2. So therefore, our sine of of 7 pi over 6 is negative 1/2. So this now becomes inverse sine of negative 1/2. Now we're going to try and figure out where is sine equal to negative 1/2 from only these two quadrants, because they gave us the inverse sine in the original problem. And that is the key. We'll talk about that more in just a moment. So we think about where sine is negative 1/2. Sine is negative 1/2 over here, and sine is negative 1/2 over here. 7 pi over 6 and 11 pi over 6. Of those two, the only one that's in the proper quadrants is 11 pi over 6. So we get that this is equal to 11 pi over 6. Or do we? And the answer is no. Because 11 pi over 6 is not between negative pi over 2 and positive pi over 2. We need to make an adjustment here. So remember, when you go into quadrant 4, we're not going to go around this way with inverse sine. What we're going to do is we're going to go backwards. And how far backwards do we have to go? We have to go backwards pi over 6. That's our reference angle. And so it turns out that this thing is going to be equal to negative pi over 6. This is the correct answer for inverse sine of 7 pi over 6. So not only does it not give us just the 7 pi over 6 by canceling out the sine and the inverse sine, it doesn't even give us the 11 pi over 6 that we would normally write. It has to give us negative pi over 6. You have to just look at the reference angle and say, okay, to be numerically between these two values, I have to go backwards pi over 6. Let's take a look at another variation on this. Let's do inverse sine of cosine 2 pi over 3. So this is another variation that you can have within these. Again, notice our inverse function is on the outside, but notice that the regular function on the inside doesn't even match the inverse on the outside. So you couldn't even try and cancel these things even if you wanted to. So how do we do these? Again, we work from the inside out. 2 pi over 3 is over here at negative 1/2 comma square root of 3 over 2. The cosine value is negative 1/2. So this gives us inverse sine of negative 1/2. And we saw from just a moment ago that inverse sine of negative 1/2 gives us the 7 pi over 6 and the 11 pi over 6. But really what we're going to put as our answer is our negative pi over 6 again. So this is another variation that actually comes out to the same answer, but it looks very, very different when it's set up. So again, work from the inside out, evaluate the inside, and then figure out where the outside function, the regular version of the outside function, in this case sine, where is sine equal to that value in the proper quadrants and with the proper numbers. Okay. The other variation that we can have is we can have the inverse on the inside. And we can do things such as cosine of inverse tangent of 3/5. Notice now our inverse function is on the inside. Remember, folks, that what the inverse function does is it takes the ratio of sides of the right triangle. In this case, with tangent, it's taking opposite over adjacent, and it returns an angle. This tangent inverse of 3/5 is an angle theta. And so what we're going to do is whenever we have the inverse function on the inside, we are going to draw the picture of our angle. So what two quadrants is tangent positive in? Well, tangent is positive in quadrant 1, and tangent is positive in quadrant 3, where sine and cosine are both negative. But of those two, where does the inverse tangent function actually reside? It actually resides in quadrant 1. So we know that we must be in quadrant 1. Cannot be quadrant 3. Here's our theta. Tangent is opposite over adjacent. We can use the Pythagorean theorem, a squared plus b squared equals c squared. So c is equal to plus or minus the square root of 34, and since this is our hypotenuse, it's always going to be positive, regardless of what quadrant we're in. So now we have our triangle. This is our theta picture, and what they're asking us to do now is find cosine of theta. Well, now that we have the picture, cosine is just going to be adjacent over hypotenuse, so this is just going to be 5 over the square root of 34, which when you rationalize it becomes 5 rad 34 over 34. So remember, whenever the inverse function is on the inside, you draw the picture of the angle, and then you take the outside function of that picture, of that angle. So let's take a look at another quick one. Let's take a look at tangent of inverse sine of 1/3. So we have the inverse on the inside. That's our theta. That's our picture. So we're going to draw the picture. Inverse sine is quadrant 1 and quadrant 4. Of those two, sine is positive in quadrant 1. So again, we have a quadrant 1 angle. And so opposite over hypotenuse is 1 over 3. That makes this the square root of, that makes this 2 square root of 2, All right, 1 squared plus b squared equals 3 squared, so 9 minus 1 is 8. That gives us the square root of 2, or 2 times the square root of 2. Let me actually write that out for you. So b squared is equal to 9 minus 1 equals 8. So b is equal to plus or minus 2 rad 2. And we're in quadrant 1, so obviously it's positive. So now there's our theta picture. And so now we want tangent of that picture. Tangent of that picture is opposite over adjacent, which when you rationalize it becomes square root of 2 over 4. So that's how it works when the inverse is on the inside. Now there's one last thing conceptually that I want to talk about here, and that is, why is it that when we see something like inverse tangent of 3/5 or inverse sine of 1/3, we are only getting one answer, whereas in the last section when we were solving trig equations, when we saw inverse sine of 1/3, we were getting two answers. So why is it when I see inverse sine of 1/3, we punch this into our calculator. Inverse sine, parentheses, 1 divided by 3. We get 19.47 degrees. And that's the only answer. Whereas, if we were solving sine of x equals 1/3, and we did x is equal to inverse sine of 1/3, that would give us x is equal to 19.47 degrees, but then we would have to put that on our unit circle use our reference angle, move over to quadrant 2, do 180 degrees minus 19.47, and it would give us a second answer, which would be what, 160.53? So why do we get one answer to the first one and two answers to the second one? And so as a way of helping you understand why that is, let me go back to something from Algebra 1. If you were given x equals the square root of 4, the answer to this is 2. But if you were given x squared equals 4, and then you took it and square rooted both sides, you had to put a plus or minus in, and you got x is equal to plus or minus 2. So what was the difference between the two original problems? The difference was whether they gave us the principal square root symbol or not in the original problem. In the first problem, they gave us the symbol telling us they only want the principal square root, the positive one, therefore there's only one solution. In the secondary equation, they did not give us the principal square root symbol. Where did it come from? We put it here. To help us get x by itself. We do not get the option of throwing out solutions that actually work. Therefore, we have to take into account the positive and negative version, both. Now, up here, where did the inverse sign symbol come from in the original problem? It was given to us. When they give it to us in the original problem, they are telling us that they only want an answer from either quadrant 1 or quadrant 4 with the proper numbers between negative 90 degrees and positive 90 degrees. Okay, so we can only put one answer down. Notice on this one, the inverse sign was not in the original problem. Where did it come from? We put this here to help us get x by itself. We don't get the option of throwing out solutions that actually work. That's why we are forced to go looking for the other one. So that's the concept. It's very similar to the concept of using the principal square root. If we put the symbol in, we have to look for other possible solutions. If they put the symbol in, they are telling us they only want one answer. Okay, so hopefully that will get you through the next assignment, and that brings us to the end of the chapter. And so we'll be doing review from here on out to get ready for the quiz and the test.